Hello learner, welcome back to our course Introduction to Electric and Hybrid Electric Vehicle. This is week 3 and in this week we are talking about the hybrid electric vehicle. In previous 2 sessions we have discussed about electric vehicle and hybrid electric vehicle along with the ICE engine vehicle. In this week we will talk about another configuration of hybrid electric vehicle. Before getting into the another combination or configuration of hybrid electric vehicle, let us have a quick review of the content that we have covered in previous lecture. We have discussed about internal combustion engines, its configurations, its advantages, disadvantages and different issues and challenges associated with it. And then we have discussed about how the issues associated with the internal combustion engine can be resolved or overcome by battery electric vehicle, or in another term you can call it a electrified vehicle. In that we had a discussion on configuration of battery electric vehicles, its advantages, disadvantages and how it is helping to improve and resolve the issues associated with the internal combustion engines. Then we have discussed about hybrid electric vehicle. As we have seen, the internal combustion engine has its own set of advantages and disadvantages. Battery electric vehicle has its own set of advantages and disadvantages. So, to exploit the advantages of both the vehicle combination and to complement the weaknesses of each other, both the vehicle technology has been combined in form of hybrid electric vehicle. So, we have discussed hybrid electric vehicle and different configuration of the hybrid electric vehicle. In last lecture we have covered series hybrid electric vehicle. So, in this lecture we will dwell on another configuration of a hybrid electric vehicle, that is parallel hybrid electric vehicle. A parallel hybrid electric vehicle represents a harmonious blend of mechanical propulsion system and electric propulsion system. Plug-in parallel hybrid electric vehicle offers a compelling solution for a greener automotive future, combining the best of both the world, that is electric propulsion system and mechanical propulsion system. A parallel hybrid electric vehicle provides the extended range and familiar refueling experience of conventional vehicle with the efficiency and reduced emission of electrified vehicle. So, in that way it is bringing the advantage of both the vehicle configuration. This versatility allow parallel hybrid electric vehicle to adapt to various driving scenarios such as city driving, highway cruising and hill climbing. It provides seamless switching between or combination of power sources for optimal performance and fuel economy. As a crucial stepping stone towards full electrification, parallel hybrid empowers drivers to embrace sustainable transportation without compromising the convenience and driving experience of conventional vehicle. As one can see in the schematic of parallel hybrid electric vehicle, the major component and their function of the parallel hybrid electric vehicle remains very much similar to series hybrid electric vehicle, be it working and operation of ICE engine vehicle, electric motor, power converters, battery, etc. The difference remains in the way they are combined and meeting the objective with different operating points. So, in this you can see the different components of parallel hybrid electric vehicle, which is more or less similar to series hybrid electric vehicle. Now, coming to the architecture of parallel hybrid electric vehicle, here you can see electric propulsion system combining battery, power electronics converter and electric motors, and mechanical propulsion system combining fuel tank, internal combustion engines are parallelly coupled with a mechanical coupling. So, that is why since the electric propulsion system and mechanical propulsion systems are connected or combined parallelly, it is termed as parallel hybrid electric vehicle. The different aspects associated to the parallel hybrid electric vehicles are very much similar to again series hybrid electric vehicle. However, they offer a different set of operation. If you talk about in terms of power delivery, then in a parallel hybrid configuration, the internal combustion engine and electric motor are connected in a way to deliver a power to the vehicle's wheel either individually or simultaneously. There is a mechanical coupler that couples both the power coming from the electric propulsion system and mechanical propulsion system, and hence enabling the efficient power delivery to the wheels of the vehicle. If you talk about the operating strategies, then in parallel hybrid electric vehicles, efforts are made to operate the electric motor alone at lower speed. We will discuss this part further while discussing the modes of operation. And the IC engine alone at a higher speed, optimizing for higher efficiency and better fuel consumption along with the reduced tailpipe emission. As far as the control algorithms are concerned to control the different operating mode and working states of a parallel hybrid electric vehicle, an appropriate control algorithm is necessary to monitor and control the vehicle response, selecting the optimal power source based on the driving profile. In case of regenerative braking, when IC engine is working alone or during deceleration, the electric motor can act as a generator to charge the battery and consequently further enhancing the energy efficiency, and it adds few more miles to all electric drive of the parallel hybrid electric vehicle. Another aspect is the efficiency and the complexity compared to series hybrid electric vehicle. The elimination of the generator, as one can see in the architecture of parallel hybrid electric vehicle, we are not having that additional generator. The single motor is acting as a motor as well as generator as and when required, resulting in a single stage power conversion, increasing efficiency and reducing weight cost. However, it adds complexities in control, since the single motor, single electrical machine has to act as motor as well as generator. So, naturally it will act the complexities, operational complexities of the vehicle. Although the parallel coupling of the power source adds complexity in control, but leaves space for further research and improvement of vehicle performance, as it brings the advantage of dual power source. Both the source can have the freedom and flexibility to individually drive the vehicle, as well as both the source can combine, or both the propulsion system can combine together to enhance the power delivery to the vehicles. The major research efforts on parallel hybrid electric vehicles are focused on implementation of continuously variable transmission instead of fixed step transmission, that gives the freedom to operate the IC engine vehicle at its most efficient point at demanded torque and speed. So, let us discuss about the power flow control in a parallel hybrid electric vehicle, as both the power plants or both the propulsion systems are delivering power to the wheel. So, it is really very interesting to see how this power flow can be controlled in a parallel hybrid electric vehicle. So, not getting into much detail about the energy management side, we will discuss here the objective that should be kept in a mind while devising the power flow control or energy management mechanism for parallel hybrid electric vehicle. Okay. So, because of this parallel configuration, different power control strategies are necessary to regulate the power flow to or from different components. However, all the control strategies aim to satisfy few goals or objectives, and these goals can be maximization of fuel efficiency, minimization of tailpipe emissions, minimization of overall system operational cost, and at last, which is quite important in terms of the experience that one can get, it is good driving experience as well as good driving performance. So these are certain aspects that should be kept in our mind while devising the power control or energy management mechanism in parallel hybrid electric vehicle. The design of power control strategy for hybrid electric vehicle should have few more consideration which is quite important. The first one is optimal operation of IC engine or placing the IC engine to its optimum operating zone. The optimal operating point on the torque speed plane of an internal combustion engine can be based on maximization of fuel economy, the minimization of emission, or trade-off between fuel economy and emissions. So as we have already discussed in the previous lectures that the efficiency of an internal combustion engine is very less. So the power flow mechanism should be such that it should ensure the operation of internal combustion engine to its optimum operating zone, so that one can extract maximum possible efficiency from internal combustion engine without compromising the objectives discussed earlier. Another important objective or consideration one should have while designing the power flow control is the battery state of charge, keeping the battery state of charge to its optimum value. The battery SOC may be significantly altered during discharging or generator charging or regenerative charging. This battery SOC should not exceed the maximum limit, nor should it fall below the minimum limit for better performance and battery life. Else, getting beyond this optimum operation of battery SOC, any operation or any dealing with this battery for production of the tractive effort will have a negative impact on the battery health and remaining useful life of the battery. So this few consideration has to be taken into mind while designing and devising the power flow control or energy management mechanism in a hybrid electric vehicle. Coming to the next side or next point, to the point of hybrid electric vehicle is a operating mode of hybrid electric vehicle. Hybrid electric vehicle or a parallel hybrid electric vehicle has 4 modes of operation. Mode 1 deals with the starting or full throttle acceleration. In that particular mode, both the power plant, mechanical power plant or mechanical propulsion system and electric propulsion system share the required power to propel the wheels. Typically, the relative distribution between the mechanical propulsion system and electric propulsion system is 80-20. This 80-20 is because of the size of the mechanical propulsion system and the size and the capacity of electric propulsion system. So to the best of their capacity, they share power during starting and full throttle mode. Here one can see in starting or full throttle mode, both the propulsion system is providing power to wheels of the vehicle. Here one point is important to note: the types of transmission. The single line is representing the hydraulic connection, the arrow with the white fill represents the mechanical connections, and the arrow with black fill represents the electric connection. Please keep this connection system into your mind. All this, in all the operating modes, we keep the similar convention for hydraulic connection, for mechanical connection as well as for electrical connection. And the direction of the power flow in all the modes of operation will be shown by arrow filled with red. If you talk about the mode 2 of a parallel hybrid electric vehicle, during normal driving, the required traction power is supplied by the IC engine only, and the electric motor or electric propulsion system remains in a off state. As one can see, IC engine alone contributing power to the traction of the vehicle, and electric propulsion system remains in an idle state or off state. In a mode 3, during braking, deceleration, regeneration takes place and the electric motor acts as a generator to charge the battery via power converter. So, in this mode a good amount of energy can be recovered in form of regenerative braking, and those recovered energy can be fed back to the battery, and it can help to enhance the battery state of charge. Mode 4 deals with the light load condition. The traction power is delivered by the internal combustion engine, and internal combustion engine also charges the battery via electric motor. As one can see, the IC engine is supplying not only the power which is required for a traction, but also the additional amount of power is given to the battery for charge. So, here IC engine is doing dual task, providing tractive force as well as providing electrical power to charge the battery. So, these are the different operating modes associated with the parallel hybrid electric vehicle. In a parallel hybrid electric vehicle, it is really very interesting to see that how power coming from the mechanical propulsion system and power coming from the electrical propulsion system are combined together. As we have discussed, both the propulsion systems are connected parallel. So, it is very interesting to see how these powers are integrated with each other and how these powers are combined or coupled with each other, and the mechanism by which we combine both power coming from both the propulsion system is known as the power coupling. So, let us discuss little bit about the power coupling of parallel hybrid electric vehicle. The power coupling of the parallel hybrid electric vehicle can take place in terms of torque coupling and speed coupling. This torque coupling and speed coupling are two distinct methods for combining the mechanical power of the mechanical propulsion system and the electrical power of the electrical propulsion system. The choice of coupling method significantly impact the vehicle performance, efficiency and control strategies. Therefore, the power from internal combustion engine and electric motor are added together by mechanical coupler, as we have seen in the previous schematic. So, the power coupler is a 3-port device. Port 1 is a unidirectional input and port 2 and 3 are bidirectional input or output, but both are not or both are cannot be input at the same time. Here input means the energy flows into the device and output means the energy flows out of the device. In case of hybrid electric vehicle, you can see power integration mechanism. Port 1 is connected to the shaft of an internal combustion engine directly or through mechanical transmission, whereas port 2 is connected to the shaft of electric motor directly or through mechanical transmission, and port 3 is connected to the driven wheels through a mechanical linkage. Generally, the mechanical coupling are of two types as I mentioned earlier, torque coupling and speed coupling. So, let's have a short discussion on this torque coupling and speed coupling. In a torque coupling, the IC engine and electric motor are connected to the same shaft through a transmission system. This allows their torque output to be directly added together, resulting in increased overall torque at the wheels. However, the rotational speed of IC engine and motor are linked, which can limit flexibility in optimizing their individual operating point for efficiency. On the other side, in a speed coupling, the internal combustion engine and electric motor are connected to a different shaft or axles. Their rotational speed can be controlled independently, allowing for greater flexibility in optimizing their operating point for efficiency. However, the torque contribution from each source cannot be directly added together and are combined through the interaction of the wheels with the road. So, gear arrangement and planary transmission system are the two examples that represents the torque coupling and speed coupling. Both torque and speed coupling have their own advantages and disadvantages, and the choice often depends on the specific design goals and requirement of plug-in hybrid electric vehicle. Torque coupling is often used in an application where high torque output is a priority, such as in performance oriented vehicles or those requiring significant towing capacity. On the other side, speed coupling is often preferred in applications where efficiency and flexibility are paramount, such as in city driving or highway cruising. Some parallel hybrid electric vehicle may even utilize a combination of torque and speed coupling to achieve the best of both worlds, depending on the driving condition and operating modes. For example, a parallel hybrid electric vehicle may use torque coupling for acceleration and hill climbing, whereas high torque is required, and then switch to a speed coupling for cruising at a constant speed where efficiency is more important. So, that is all about the ways in which we combine the two power, we combine power coming from two different propulsion system, mechanical propulsion system and electric propulsion system housed in a parallel combination to drive the wheels of the vehicle, making a parallel hybrid electric vehicle. In these combinations, there are certain advantages comes, and these advantages are very much similar to the advantages of hybrid electric vehicle. Being a member of a hybrid electric vehicle, certainly it possesses all the advantages associated with the hybrid electric vehicle, and few of those exclusive advantages associated with the hybrid electric vehicle are dual power sources, IC engine and battery, optimized fuel efficiency. You can smoothly switch over between the mechanical propulsion to electric propulsion system for enhancement and optimization of the fuel efficiency. Automatic power distributions, continuous advancement is taking place in this particular configuration, so that better driving experience and performance can be achieved, which should remain very much closer to the conventional vehicle, and certainly it offers reduced emission, though the reduction of the emission is less, but certainly this configuration also contributes in the reduction of the emissions. And further, the during regenerative braking, the energy regeneration also helps in recovery of the energy during deceleration or braking. As far as the major issues or disadvantages associated with the parallel hybrid electric vehicle are concerned, some of them are limited electric only range, as the battery size is quite small. So, a parallel hybrid electric vehicle offers less electric range. Complexities and the cost, it has limited environment benefit, since the electric contribution of the electric propulsion system is very less. So, environmental benefit will also be very less. High upfront cost, because of the complexities and the power coupling, the initial cost of the vehicle will be very high, and again it has a dependency on the internal combustion engines, and it may require some maintenance for its better and smoother operation, as the internal combustion engine remains at a dominating place. So, certainly it will invite maintenance or routine maintenance in this. So, that is all about the parallel hybrid electric vehicle, its operation, working, advantages and disadvantages. So, let us have a quick comparison of the parallel hybrid electric vehicle and series hybrid electric vehicle. In a series hybrid electric vehicle, as far as the powertrain configuration is concerned, the IC engine drives a generator to generate electrical power, and that electrical power is given to the electric motor, and electric motor drives the vehicle. Whereas in parallel hybrid electric vehicle, IC engine and electric motor can both supply the wheels of the vehicle. As far as the efficiency is concerned, in series hybrid electric vehicle are more efficient in comparison to the parallel hybrid electric vehicle. If you talk about the power output, in series hybrid electric vehicle we have a limited power output, whereas in parallel hybrid electric vehicle we get relatively better power output. Series hybrid electric vehicle offers simpler design with fewer moving parts, whereas the parallel hybrid electric vehicle has a complex design with additional components for power coupling. As far as control complexities is concerned, certainly as we discussed, series hybrid electric vehicle has simple control, whereas the parallel hybrid electric vehicle has complex control. If you talk about the flexibility, flexibility with series hybrid electric vehicle is limited, whereas the parallel hybrid electric vehicle has more flexible in terms of taking power, and hence it gives the versatile performance. Series hybrid electric vehicle is quite less costly in comparison to the parallel hybrid electric vehicle. As far as the driving scenario is concerned, series hybrid electric vehicle is best suited for city driving and short trips, whereas the parallel hybrid electric vehicle is best suited for highway driving and long trips. If you talk about some of the commercialized available vehicle model for series hybrid electric vehicle, then it is BMW i3 and Chevrolet Volt, whereas for parallel hybrid electric vehicle, Toyota Prius and Honda Accord Hybrid. Toyota Prius is one of the most talked and popular hybrid electric vehicle. We will have some discussion on this to see how this parallel hybrid electric vehicle is bringing better benefits and advantages in hybrid electric vehicle segment. So, these are some of the commercially available example of parallel hybrid electric vehicle. As I mentioned, Toyota Prius is the front runner in this configuration. Another one is a Honda Accord, next one is a Hyundai Sonata, and then Kia Nitro. These all four vehicles are based on the parallel configurations, and they are doing they are getting good attention in the market. So, let us have a quick discussion or a kind of case study on one of these model, which is Toyota Prius, as it is one of the most popular parallel hybrid configuration. So, the Toyota Prius, a pioneer in parallel hybrid electric vehicle, stand as an iconic symbol of the parallel hybrid electric vehicle, showcasing the successful integration of the electric propulsion system and mechanical propulsion system for enhanced efficiency and reduced emission. As far as the technical specification is concerned, we will take example of Toyota Prius 2023 model. The drivetrain configuration is a parallel configuration. It has 1.8 liter 4 cylinder petrol engine, and it has 70 HP permanent magnet synchronous motor with it. Both electric propulsion system and mechanical propulsion system both combined produces power of 121 horsepower, and its transmission is electronically controlled continuous variable transmission. It uses the lithium-ion battery. Capacity varies from model to model, and if you talk about fuel economy, it has 57 mile per gallon for city, and it gives somewhere around 56 to 60 mile per gallon for highway, and it also comes under the category of ultra low emission vehicle in comparison to the conventional IC engine vehicle. So, the Prius combines the power of both the plant and optimize the performance and efficiency in various driving scenarios. It delivers all the advantages of hybrid electric vehicle, and it has a good market impact and future outlook. It has played a crucial role in popularizing the hybrid technology and demonstrating the feasibility of mainstream electrified vehicles. The Toyota Prius continues to evolve, incorporating advancement in battery technology, power electronics and hybrid system control strategies, which will further help in improving overall efficiency and performance. At the same time, it might help in the reduction of tailpipe emission. As a pioneer, the Toyota Prius has paved the way for more sustainable and electrified automotive future. Since the Toyota Prius is one of the successful model, and that is why that has been taken and considered for the discussion in this lecture. If you compare the Toyota Prius with the Honda Accord, so both the vehicle has a very much matching performance. Honda Accord has a higher rated IC engine, whereas at the same time it also has a higher rated electric propulsion system. 2 PMSM traction motor is involved in Honda Accord. And if you talk about the combined power, the Toyota Prius offers 121 horsepower, whereas the Honda Accord offers 204 horsepower. If you talk about the fuel economy, we have seen the Toyota Prius offers somewhere between 55 to 60 mile per gallon, whereas the Honda Accord offers somewhere between 45 to 51 mile per gallon. Certainly it is obvious, as you can see the IC engine is highly rated in Honda Accord, and that is why it has impact on the mileage, and it is offering less mileage in comparison to Toyota Prius. Both comes under the ultra low emission vehicle category, right. So that is all about the parallel hybrid electric vehicle and associated technologies to it, and discussion on some of the commercial model available in the market for based on the parallel configuration. So let us have few quiz based on the discussion of parallel hybrid electric vehicle. So the first quiz that we can take is, what does the term parallel hybrid in vehicle refer to? A vehicle that uses solar and wind power. B, a vehicle that has two electric motor working together. C, a vehicle that can be powered by both an internal combustion engine and electric motor simultaneously. Or D, a vehicle that operates only on electric power. So if you have gone through the lecture carefully, certainly you can answer this question. So the answer of this quiz is C, a vehicle that can be powered by both an internal combustion engine and an electric motor simultaneously. The another question that we can take is, in a parallel hybrid electric vehicle, when is the electric motor most likely to be used? During high speed, during low speed, only when the battery is fully charged, or only when the internal combustion engine is turned off? Though this question seems bit tricky, but if you have heard the lecture carefully, you will be able to answer this quiz, and the answer here is B, during low speed city driving and acceleration, the motor electric motor can be switched in for getting better efficiency and less emission. Another quiz that we can take is, how does a parallel hybrid electric vehicle improve fuel efficiency? These are the following options. So if you go through this option, certainly you can understand that the parallel hybrid electric vehicle improves the fuel efficiency by optimizing the use of both the electric motor and internal combustion engine depending upon the driving condition. So in this lecture, a parallel hybrid electric vehicle has been discussed along with its architecture, working, operating mode, followed by advantages and disadvantages. The concept of power coupling mechanism has been elaborated. Series hybrid electric vehicle and parallel hybrid electric vehicle have been compared, and a brief overview of Toyota Prius has also been discussed. So, that is all related to the parallel hybrid electric vehicle. I hope this lecture have helped the learner to deeper their understanding on parallel hybrid electric vehicle. So, remain curious. Happy learning. Thank you.